Changing the loading is one of the most frequently used changes because it often gets us to situations where we can find predetermined formulas for internal force and deformation, and because we can typically predict whether the effect creates an upper or lower bound on the detailed analysis result. The goal of approximating the loading is to turn it into something easy to analyze, say a uniform distributed load or a point load. The most accurate approximation typically uses an equivalent load. That means the total force is the same, it is just configured differently. How the load moves tells us the effect. If we move load toward the supports, it reduces the peak moment and the peak displacement. In our example here, there was a point force at midspan along with two other point forces. When we convert those 3 point forces to a uniform distributed load, we are moving force away from midspan, so the peak moment drops. In fact, in this case, the peak moment with uniform load is 25% smaller than the peak moment with the 3 equivalent point forces. Similarly, the peak displacement is smaller because we moved load toward the supports. 22% smaller in this case. So moving load toward the supports results in a lower bound for peak moment and peak displacement. Conversely, consider what happens when we move the load away from the supports, like in this second example. By converting the 3 point forces into an equivalent single point force at midspan, we moved load away from the supports. The result is a larger peak moment, 50% larger, and the peak displacement increases by 26%. So moving load away from the supports results in an upper bound for peak moment and peak displacement. This holds true for cantilevers also. Consider this cantilevered beam with a triangular distributed load. The equivalent uniform load would be omega naught over 2. To make this change, we are moving some of the load away from the support and out toward the free end. Therefore, the peak moment and displacement should increase. Indeed, they do. The peak moment increases by 50% and the peak displacement increases by 87%. So the key is not whether load is moved toward the ends or toward midspan. It is whether the load is moved toward or away from the supports. That shows us how to predict the effect on peak moment and displacement, but what about shear? In all of these cases, the peak shear has been unchanged. So what affects peak shear? Approximating the loading will only change the peak shear if we move load away from one support and toward another. For the simply supported beam example, we moved an equal amount of load an equal distance toward each support. So there was no change in the peak shear. For cantilevers, no matter where we move the load, we are not moving it toward a second support, so there is no change in the peak shear. So when might approximating the loading cause a change in peak shear? Whenever we have a beam with multiple supports and loading that is not symmetric between the supports. Converting to a uniform distributed load or a point force at midspan will cause the peak shear to change. For example, consider this simply supported beam with uniform load over only part of the beam. If we convert that load to an equivalent uniform load over the entire beam, the magnitude of the distributed load is lower, and we have moved some load from the right side of the beam to the left side. Therefore, we are increasing the peak shear at the left support to where we have shifted load, and we are decreasing the peak shear at the right support from where we have shifted load away. Uniform distributed load on a simply supported beam happens a lot in real structures. Joists or beams supporting a one-way slab behave this way. So knowing the peak shear and moment for this situation is very helpful. To figure out the peak shear and moment, we need to start by finding the reactions. There are vertical reactions at each support. Let's call them A and B. If we sum moments about B, we get a positive contribution from AY and a negative contribution from the distributed load acting at L over 2 from B. When we solve for the reaction at A, we get omega L over 2. The peak moment for this beam is at midspan. We learn how to prove that in a later chapter, so for now you will need to trust me. For our free body diagram, we cut it at midspan. Let's keep the left half since we have the reaction at A. The length is L over 2, and there is uniform distributed load along the body. At the cut, there is unknown shear V and the unknown maximum moment M. Summing moments about the cut, we have a positive contribution from AY acting through L over 2, a negative contribution from the distributed load, which acts through L over 4, and a negative contribution from M at the cut. When we solve for the maximum moment, we get omega L squared over 8. That is a formula worth memorizing. The peak moment for a simply supported, uniformly loaded beam is omega L squared over 8. Peak shear is at the support, so for a simply supported beam with uniform load, the peak shear is omega L over 2. Although simply supported beams with a single point load at midspan are not as common in real structures, we use this as an approximate loading often. Therefore, it would be helpful to derive the peak shear and moment for this case as well. Again, let's label the reactions AY and BY. To find the left reaction, we sum moments about point B. We have a positive contribution from AY and a negative contribution from the point load P. Solving, we find that the left reaction is P over 2. For this loading, the peak moment is directly under the point load, so it is at midspan. Therefore, we draw a free body diagram of the left half of the beam. We have the reaction at A. It doesn't matter to the moment calculation whether we cut to a little left or right of the point force, so let's say we cut the beam a little to the left. At the cut, we have the unknown shear V and the unknown peak moment M. We sum moments about the cut. We have a positive contribution from the reaction acting through L over 2 and a negative contribution from the unknown moment M. Solving for the maximum moment, we get PL over 4. As a comparison to the beam with uniform load, consider this. If we took the equivalent force from the uniform distributed load and lumped it as a point force P at midspan, we get a resulting peak moment of omega L squared over 4. So we have a clear demonstration that moving load away from the supports causes an increase in moment. Now for the peak shear. It happens at the supports, so V max is P over 2.